I'd like to show you how to analyze an air compressor in MATLAB. And so what I've done is I've started with my basic air tables demo MATLAB file, you save as, and then I've started that brand new file to show you how to basically analyze a basic industrial air compressor within the MATLAB environment. So let's go ahead and get started. Here's a picture of this is basically an industrial centrifugal air compressor, relatively high capacity, used in manufacturing and industry for delivering compressed air to processes that require compressed air, to instruments that require compressed air to operate, and to actuators that use compressed air to adjust valves, position arms, and various processes like that. And so here is a frequent request by managers in the manufacturing environment. I got questions like this very frequently in my workplace. Here's the request from a manager. Determine the daily operating cost for an electric motor-driven air compressor producing 28 cubic meters per minute of air at the inlet with inlet conditions 25 degrees C and 100 kPa, very much atmospheric situation, and an outlet pressure of 750 kPa, and an isentropic compressor efficiency of 80%. The cost of electric power is 10 cents per kilowatt hour. Now, the manager is also asking a couple of additional questions. Determine the actual power required to drive the compressor. Well, we'll need that to determine the daily operating cost anyway. And then the next request is also determine the outlet temperature of the air leaving the compressor before after cooling. And that's a reasonable request as well, because we need to plan how will we cool this compressed air, this hot compressed air, before sending it out for use in our piping so that it will be about at the temperature of the surroundings. Oh, and the manager says, and I need your report by lunchtime today. So we'd better get moving on analyzing our air compressor. Why is this manager asking us this question in the first place? The answer is it's a frequent request because managers are always looking at ways to reduce operating costs. And this is a classic one. How do we reduce the use of compressed air in our manufacturing facility? So a manager might say, wow, how much money could we save in a year's time if we cut our compressed air usage in half? Or if we cut our compressed air usage by 25%. Those are reasonable questions to ask, and it's up to a mechanical engineer to answer those questions because there's going to be few, if any, others within your workplace that would be able to answer this question quickly without trying to find somebody else that could answer the question. So let's get started. Let's start with a sketch and plan our work. Well, here's our sketch of our compressor. See how it looks similar to the photograph of our compressor, coming in at state 1, leaving at state 2 with compressed air. The compressor, we're squeezing the air, we're making it smaller, specific volumes getting smaller, pressure is going up. We recognize air, we're going to treat it as an ideal gas, and for this analysis, let's say we're going to treat it with variable specific heat, and that's the same as saying we're going to use table A22 to evaluate our properties that we need for our thermodynamic analysis. Things like H, we're going to need H. Variable specific heat, that's for air, use table A22, all right? Another thing, looking ahead, we're going to need to calculate the power, but we're only given the volumetric flow rate at the inlet, meters cubed per minute, that's AV1. So we're going to need m dot. We need mass flow rate. How will we get mass flow rate? That's right. Mass flow rate is the volumetric flow rate divided by the specific volume. Remember our heads. Let's see. Specific volume, we have an ideal gas. We immediately remember the ideal gas equation of state. V1 is R T1 over P1. As long as we've got R, we've got T in absolute temperature, pressure, and kPa. That's going to give us specific volume in cubic meters per kilogram. Okay, so we've got M dot. Now let's move over to our temperature entropy diagram to plan what we're going to do on the thermodynamic analysis. First thing we'll do is look at the isentropic process, 1 to 2I for the compressor, and we will determine how much work it takes to drive the compressor. In other words, W dot over M dot, that's going to be a negative number, W isentropic. Okay. Let's see. We have a general idea how to do that. We'll study the isentropic process, get W isentropic. Then we will apply that compressor efficiency, 80%, to determine W actual. Now let's see. Will W actual be, it'll be a larger negative number than W isentropic, because just your common sense tells you it will take more power to drive a real compressor than driving an isentropic reversible adiabatic compressor. Okay, I think we're doing pretty good. I think we've planned. No, let's look at the first law for any steady state, steady flow open system, just to remind ourselves what we're doing. Okay, we've got a generic open system. The mass inflow rate, M dot in, exactly equals M dot out. That's continuity equation. For our problem, we've got an fully insulated compressor. Q dot in will be 0. W dot out, that's what we're seeking to find, and we're expecting it to be a negative number. In other words, power required to drive the compressor. So our first law, Q dot in, that's 0, insulated, minus W dot out, that's what we're seeking to find, equals M dot. We see a path forward for getting that, times H2 minus H1. We're going to need those. Kinetic energy change, for this analysis, we're going to say kinetic energy change is negligible between state 1 and state 2, and certainly potential energy change of the air from state 1 to state 2 is certainly 0. All right. First thing we'll do is study the isentropic process, 1 to 2I, to determine W dot out isentropic first. Then we will apply our turbine efficiency definition to get a larger negative number, W dot out actual, and then we'll calculate the cost on a daily basis to operate this compressor. Okay, so now I think we've planned enough. We've drawn a sketch, we've planned our general approach, we've reviewed the first law, we're ready to go live into the MATLAB environment. Okay, so I'm going to bring up MATLAB. And the first thing I bring up is my air prop functions _SI, sort of my demo file. I hope you've watched my video that shows you how to use this demo file of using basically the MATLAB version of table A22. Hope this looks familiar to you. Let's look quickly. Here's the reference and what's going on. Here are the list of functions that are available to us in MATLAB that I've created for myself and for you to share. Okay. Remember the demo file, these were demos of how to call the various functions that are available in MATLAB created by the user, me. Okay. All right. So this was our basic demo file. The next thing I did was I went to save as. So save as. I came up with a new file name. Now I've already done the work, and so I'm not going to start from scratch. So you get the idea of save as, the basic file. And what I did was I saved it to a file called AirCompressorCostDemo.m from MATLAB. All right, so here we are. So now let's look at this air compressor analysis file. I'm starting out with a lot of comments. Here's my file name, AirCompressorCostDemo.m. I am signing it, right? So that's me. And I did this work on October 4th. Okay. And let's see. Here's the list of functions that are available. I just left that in just for, as I was going in and solving the problem, I would refer to this list of functions, be sure I had the right syntax for the inputs and outputs. The next thing I did was I typed in my approach for solving this problem. Okay, and so we've already verbally talked about our approach. So, but you can see that I'm trying to work down the page and show others how did I get a solution. And now I've removed the part of the demo. I've removed the demo part of that original file, and I'm putting in the part that I'm calling solution. All right. So now we've got to remember, what are we supposed to do first? First, let's work on the mass flow rate. So let's get the specific volume at state 1 first. V is RT over P. Oh, I need R. All right. Well, I remember R bar. Here we go, with units. I remember the molecular weight of air with units, kilograms per kilomole, 28.97. And so R for air is R bar over the molecular weight. Okay, I've got R for air. Yay. The next thing we'll do is find V1 and also write down. So what are we given? We're given AV1, the volumetric flow rate going into the compressor in cubic meters per minute. Now, looking ahead, I know that I'm going to want mass flow rate in kilograms per second. So the first thing I'm going to do is transform the variable AV1 into the same variable name AV1, but with the units meters cubed per second. So do you see what I did here? I just plopped down AV1 is 28. That's my volumetric flow rate. And then divided it by 60 to get cubic meters per second. And I'm trying to explain that in my solution. Now I'm writing in MATLAB variable P1 for pressure. Okay. I'm put 100 kPa. Now, next variable, T1C, that for me, that's kind of like temperature 1 in degrees C. Well, that's 25. So next one, so I'm going to call T1, that's my next variable. T1 is T1C, which was 25, plus 273. So you see, I'm trying to explain my work as I go. I'm trying to document what I'm doing so others can follow along, not just myself. And I might remind myself, because I might get this nearly similar question by a different manager with slightly different inputs next month. All right. So here's V. Here is V1, specific volume at state 1, RT over P, ideal gas law. Okay. Cubic meters per kilogram. So now I can solve for M dot. It's the volumetric flow rate divided by the specific volume, AV1 over V1. So yeah, the selection of variable names sort of makes sense. Okay. So now we've got the mass flow rate, M dot. Now let's analyze the isentropic process, 1 to 2i. Perhaps we would be looking over at a sheet of paper for our sketch, but I think you've got a mental picture of it. Process 1 to 2i. What will we do? Well, the first thing we're going to do is, let's see, we've got, I'm going to have to refresh my memory on what I have here. I've got P1 is 100 kPa and P2 is 750 kPa. Okay. T1C, oh, I see that, look, now I am repeating my temperature here. That's not necessarily very good practice, but I see that I have done that, okay? So I'm repeating T1 is, in absolute temperature, is T1 degrees C, okay? Now what am I doing here? The next thing I'm doing, isentropic process. What I'm trying to find is T2I. So I remember that for an isentropic process for air, variable specific heat, I remember that P2 over P1 equals PR2 over PR1. Okay. And so now it's coming back to me on what I'm doing. Okay. First thing I'm doing is I'm finding PR1. It's a function of inlet temperature, T1. So I'm calling for PR. It's a function call. PR given T, non-dimensional, use with T1 the input. So I've got PR1. Next step, I'm solving for what is PR2 because I have P2 and P1. I had to refresh my memory on what I was doing on my code, right? I'm solving for PR2, PR1 times P2 over P1. So now I've got a number for PR2. Wow. Okay. So let's see. Now I've got to find the isentropic temperature T2I. All right. Well, let's see. How would I do that? I can use a function call. I've got PR2 and there's a function call called T of PR, TPR, degrees K. All right. So that's find T given PR. So I'm making this function call with the input of PR2. So it is back calculating. This function down below in MATLAB is back calculating T2 isentropic. So T2 isentropic is that function call with the input of PR2. Okay, so I'm making some progress. Okay. Now, okay, here we go. So I found T2 isentropic. The next thing I'm going to do is apply the first law for the isentropic process. So I need H2 isentropic. I just found T2I. So I'm going to use another function call, HT, kilojoules per kilogram, with the input of T2 isentropic, and I'm going to assign that function call to the variable H2I. Okay. Now, so now we've got H2I. I did not look up H1 yet, so I will now look up H1. H1, I'm going to use that function call HT, H given T. HT, kilojoules per kilogram, with the input of T1. So H1, MATLAB variable H1 equals that function call with the input of T1. Okay. Now I've got two values of H. Great. Okay. I'm trying to explain. So thank goodness I'm putting in these comments, or I wouldn't even be able to follow my own work, even though I did this work on October 4th, and today it's October 22nd. I couldn't remember this computer code in that time period. Okay. I'm using the first law. Got off track a little bit. W isentropic. Okay. This is the first law. Remember that Q is 0. So W isentropic is going to be H1 minus H2I. So now we have a number for W isentropic, W dot over M dot. I'm just preparing this to report to the command window my numerical result. Okay. Now, next comment, determine the actual work. So I'm entering the compressor efficiency, 0.8. I remember my definition of compressor efficiency so that W actual, WA, is WI divided by compressor efficiency. It's going to be a bigger negative number. Okay. Now, we're doing great. So we've got WA, we have M dot. A little further down, we've got everything we need to calculate the compressor power. But now let's work on that actual outlet temperature, T2A. We're going to write the first law again for the actual compressor process and solve for H2 actual. So do you see that this expression right here, this MATLAB expression, H2A equals H1 minus WA, it's not just a formula, it's an expression of the first law rearranged, but so it's using the first law. H2A equals H1 minus WA. So we found H2A. We're seeking to find T2 actual. Well, let's use one of those function calls. Let's use TH. So T given H, we have H2 actual. Okay, there's our input, H2 actual. We're going to assign that to MATLAB variable T2A. We'll write that out to the command window to check our work, be sure it makes sense. And now we're getting near the end point. Determine the actual power required. And so the power required is going to be negative WA. That's to flip the sign of the actual work out. Flip the sign. Power required is minus WA times M dot. We have both of those. So let's check our units. WA, kilojoules per kilogram. M dot, kilograms per second. So our units are going to be kilojoules per second. That's kilowatts. And I've written that out in a comment just to be absolutely sure, remind myself that I've got my units straight. Okay. So there's power required in kilowatts. Okay. How about the energy required? Well, our time is 24 hours and we're operating steadily at a rate of power required kilowatts. So kilowatts times hours will have units of kilowatt hours. And so I'm calling MATLAB variable KWHR, all in caps. That's my MATLAB variable name. So that's how many kilowatt hours it takes. And we were given in the problem statement cost per kilowatt hour. So my MATLAB variable name is cost per kilowatt hour, all strung together, equals 0.1. That's dollars per kilowatt hour. Okay, so the cost now, MATLAB variable named cost, equals cost per kilowatt hour times kilowatt hours, or daily cost. And there we go. And so you see that along the way, I hope you've noticed that I've been preparing output to go to the command window. Okay. And so I'm marking, there's the end of my analysis. And since I destroyed all of the demo function calls in my original file, you see all that's left is my function library, and you just leave all this stuff alone. Whether you do or do not need all of these functions, there's just enough functions there that you need. So you don't need to destroy functions that you don't need to use. You can just leave them sit there. Okay. All right. So there is step by step how I perform the analysis. And now I'm moving my zoom menus around so I can get to the run button. So I'm going to click run. Okay, so here's my command window output. I solved for T2 isentropic, 526K. Okay. I found H1 and H2. They look very reasonable. I found W isentropic to be a negative number. I found W actual, kilojoules per kilogram, to be a more negative number. Makes sense. Okay. I found M dot, 0.5457 kilograms per second. Let's see, what does it say here? At a volumetric flow rate of 0.467 cubic meters per second. I determined that the power required is 159 kilowatts, 159 kilowatts required. And so that gives me a daily cost of $380.75. So about $381 per day to operate this air compressor. So that makes it, if we could cut that in half, that would represent some significant cost savings for us in our manufacturing environment. So that is our MATLAB model for our air compressor analysis. Now let's see. Oh, I should show you. And if you say, well, that's kind of cool. I'd like to see how that works myself in MATLAB. So let me show you how to possess this file. I'm going to go to my browser, and here's Jay's Toolbox. We're at jaystoolbox.vt.domains, my public website. Anybody can access this website. So let's scroll down, drop down the Toolbox menu, and go to MATLAB. All of my MATLAB files that I'm sharing with you folks is on this one page. So let's scroll down and see if we can find this compressor analysis demo. Here's air props. Here's air props SI. That's what I used as a save as. Here it is, air compressor MATLAB. And so air compressor operating cost demo. All you need to do is click download, and you will be able to possess this MATLAB file. Now, there is one little trick. I had to save these MATLAB files as file type .doc. It's the only way I could store or post them to my website. So when you open this, once you download the file and open it in Notepad, you have to save as .m file type in order to make it the MATLAB file type. So MATLAB, so you can load it in MATLAB. So that's a little trick. So that's how you can possess this file. You can run it, click the run button, and sort of see how I solved this compressor analysis problem. Okay, now let's see. I'm going to go back to PowerPoint. We've gone live. We've sort of reviewed kind of step by step how it's solved in MATLAB. Here's the command window output. Oh, and now addressing your manager's request. I would take a screenshot of this command window output, and I would attach that screenshot to an email. I'd write a little narrative response to my manager. I would not just put, please see the attached. That's terrible form. A little email that's respectful, summarizing what you understood that was requested, sort of a bottom line, say, I've determined that the daily cost of operating the compressor is that amount. I believe I did not replace, that is a stale screenshot because I had made a mistake in my computation, and I found and corrected it. So this is a stale screenshot of the daily cost. I think we had $300 and some in checking my work. I did find an error as I was checking my work, but basically you get the idea that the screenshot would be attached to an email, very short narrative saying the daily cost is $301 today, and that'll fulfill your supervisor's request well before lunchtime. I showed you how to get this file. I am happy to report that the file that I have posted to my website is the corrected file. Now, because I showed you a stale screenshot of the command window output, I'll tell you what my mistake was. Originally, as I was blasting through the analysis, I said that m dot equals the volumetric flow rate times the specific volume. And as I was checking my work, I looked at it and said, wait a minute, I need to check my units of volumetric flow rate times specific volume. Well, those units don't work out right. And I remembered, oh my gosh, it's got to be volumetric flow rate divided by specific volume. So at the last minute, I caught that mistake. And then it's easy to correct in MATLAB, isn't it? Just change a star to a slash and rerun it. So that is one of the great advantages of MATLAB over hand calculations. Okay, so you get the idea. There is a power of save as. So you can take that original air properties MATLAB file, save as, and start solving problems and utilizing those air property function calls that I'm sharing with you. Of course, it's always important to start with a sketch and plan your solution outside of MATLAB. That we can't replace the hand-drawn sketch or setting down a little solution plan before you start coding in MATLAB. And it's important to document your work outside MATLAB. Like I say, the sketch, the solution plan, statement of the first law, those types of things. and then documenting your work inside of MATLAB with lots and lots of comments, like I'm trying to demonstrate to you. And then, of course, finally, a reminder that you really need to understand the fundamentals of thermodynamic properties like H, like PR for isentropic processes, and also a good understanding of the first law, continuity, and mass flow rates. So you've got to have those fundamentals down before you just start banging away in MATLAB. Okay, I'm a little embarrassed by my the stale command window output that I had in my PowerPoint, but I think we'll all survive. And I hope this helps you understand how you can use MATLAB to solve thermal, fluids, and heat transfer problems.